Hello everybody, my name is Iman at SAD. Welcome back to my YouTube channel and welcome back to the final part of chapter 7. Today we're going to be talking about elimination reactions, specifically E1 reaction, since we haven't covered that yet. Now, some quick notes, just a friendly reminder here. All right, these are some of the most important two tables or two figures that you need for this chapter. All right. It is super important that you commit these to memory, that you understand these fully, all right? Spend some time observing, taking notes, making flashcards, making sure you understand how to characterize all of these groups and what they will result in terms of reactions and then products. All right, now, something to keep in note, and this will make sense, as we will cover doing elimination and substitution reactions with different groups besides alkyl halides. All right, and we have here a hierarchy of the best leaving groups. All right, obviously our halogens are up here, followed by water. All right, this is a tosylate group, which is also really good. Your alcohol groups are not very good leaving groups. All right, so make sure you keep that in mind as we progress through this chapter. All right, now, if you remember, in E2 reactions, a hydrogen is abducted and a double bond forms between the alpha and beta carbon after the loss of a leaving group. This happens all in one step. But now, depending on the base, instead of an E2 reaction, you might actually get an E1 reaction. In an E1 reaction, the same thing happens, but in a different order. The leaving group leaves first, and then hydrogen gets abducted by a base, and then your double bond forms. This happens in two steps with the formation of a carbocation intermediate. Now, like SN1, the rate determining step is the first step, which is loss of a leaving group because that step has the highest energy state. The rate determining state is said to be unimolecular because it only involves one chemical entity, and the rate equation is only dependent on the concentration of our substrate. So it's a first order reaction. Now, E1 and SN1 reactions are very similar in the fact that, look at this, they're happening in two steps. All right, the rate equation only depends on the alkyl halide, concentration of alkyl halide, and you're forming carbocation intermediates that can potentially rearrange. All right, so those are all good things to keep in mind. All right, now when you are solving problems after your halogen leaves in an E1 reaction, you follow all the same steps you did in E2 to draw all the products. The only caveat you should keep in mind is, again, the possibility of carbocation rearrangement after leaving group. All right, so let's go ahead. Let's dive right into a few practice problems here. Here's our alkyl halide. All right, here's our alpha carbon. All right, first step is loss of a leaving group. So our chlorine is going to dip. All right, it's going to go away minus chlorine. And what we form here is a carbocation at that position. Now, this is a tertiary carbocation. That's the most stable carbocation. So really, there's not going to be any rearrangement here. Now, look at our nucleophile. All right, this is in the form of ROH, okay, which is, by the way, a weak base, weak nucleophile. All right, weak base, weak nucleophile. Elimination reactions tend to happen at alpha carbons that are primary or tertiary substituted. All right, so keep that in mind. Just a friendly reminder. All right, you're going to get elimination reactions with weak bases, weak nucleophiles. ROH, by the way, where R can be ethyl, methyl, anything else. All right, any alkyl chain, honestly, is a weak base, weak nucleophile, and you need an alpha carbon that's secondary or tertiary for it to proceed. Now, of course, we're going to get SN1 products here, but we're just going to draw our elimination product, our E1. All right, this reaction gives E1 and SN1. All right, so we have our tertiary carbocation here. Now, what can happen is we can form a double bond there between the alpha and beta position right here, and that is our E1 product. Now, our SN1 product would look like this. Just if you're curious, we're going to draw it as well. All right, OR, where R is all of this. I don't feel like writing it out. All right, fantastic. Let's do another one. Why not? All right, this one says one of the products that results when 1-bromo 2,2-dimethyl cyclopentane is heated in ethanol is shown below. Give a mechanism by which it is formed and give the name of the mechanism. Fantastic. So it tells us what we're starting off with. We're going to go ahead and draw this guy right here. All right, 1-bromo 2,2-dimethyl. And we're going to go ahead and draw the wedges and dashes. All right, first step, and it's going to be treated in ethanol. All right, ethanol is a weak base, weak nucleophile. All right, it's a weak base, weak nucleophile. All right, and our alpha carbon is secondary. All right, so we have a weak base, weak nucleophile. This is secondary. We're going to get E1 and SN1 reaction going on. Obviously, we're forming a double bond, so we're only going to be working with our E1 reaction here to get to this final product that we are aiming for. All right, now the first step is loss of a leaving group. So what happens here, ooh, that's ugly. I really should have gotten better at drawing before starting this YouTube channel, but alas, you will have to deal with my ugly pentanes and hexanes and all that good stuff. All right, we formed a carbocation here. Now this is secondary. So what can happen is, you guessed it. Ooh, sorry. You guessed it, methyl shift over. All right, this is going to give us, and we're going to write here just so we remember, methyl shift. All right, what that's going to give us is this. Now we have a methyl here, and now we have a tertiary carbocation. Fantastic. Now, what will happen is obviously our ethoxide will come in. All right. Or our ethanol will come in. All right, and it's going to, our ethoxide actually, oops. Our ethoxide is going to come in. All right, and what it's going to do is it's going to steal a hydrogen. All right, it's going to steal the hydrogen here. The hydrogen will dump its electrons here, and we're going to form a double bond there. All right, and so we have obtained the product that they wanted us to. We have drawn the mechanism, and this is an E1 reaction. Fantastic. Now, we're going to do this problem. We did this in our mixed problem sets of SN1, SN2, and E2. All right, we drew these two products, but what we can do now is figure out how to draw the mechanism for the E1 product here. All right, so that's what we're going to focus on for this problem now, since we've already done the rest of the problem. Okay, what happens is, first step is loss of a leaving group. All right, so you form a carbocation here. Now, what can happen is actually what can actually happen here is a hydride shift. All right, there's a hydrogen here that can move over here. Fantastic. All right, and what we get then is this tertiary carbocation. Now, our alcohol group, or I mean, our OR group, okay, can come, steal a hydrogen, dump its lone pairs, all right, and we can form a double bond there. And guess what? That would give us this product that they were interested in. All right, fantastic. Now, with that being said, all right, we've covered E1, E2, SN1, and SN2 reactions. We've done plenty of practice problems for all. All right, now what we want to do is, what if we move away from alkyl halides as leaving groups? What if instead of having chlorine, bromine, or just iodine, working only with those alkyl halides, what if we had an alcohol group on there? We can still do our substitution and elimination reactions, but we have to keep something in mind. All right, if we look at alcohol groups, for example, they are bad leaving groups, but they can be converted into good leaving groups through two different routes. They can be converted into tosylates using TSCl and pyridine, or they can be converted into water using some strong acid or sulfuric acid. All right. Now, we will go through this with all 4 of our reaction now. So, what we're going to do is we're going to see this at play for every kind of reaction. And this is going to be a friendly reminder for you as well. All these pages, right? Good reminder of SN2 and all the properties of an SN2 reaction and what it requires. And of course, our famous tables here that are going to help us determine it. Right? We've done enough SN2 reactions now, right? We know that if we have, right, our alkyl halide, right, there's a halogen there, that's going to be our leaving group. So if we treat it with a strong nucleophile weak base, that iodine is going to be replaced into SH. Fantastic. But now we want to ask, well, we can have SN2 reaction with different leaving groups. For example, what if we had tosylates? All right, tosylates are a great leaving group. We actually don't have to convert it into anything. So we have our nucleophile bromine. It can come and attack here at the electrophilic carbon, and we can replace the tosylate with a bromine, keeping in mind inversion of configuration. We can also do SN2 reaction with alcohols. All right, no problem there. Okay, but the first thing that we have to do is we actually have to convert the alcohol into water. All right, and then we can do the following reaction. So with alcohols, we can also attack and substitute, say, an alcohol group, all right, with bromine. Then our bromine, after converting this into water, can come attack our electrophilic carbon, and we will get this product. All right, now here's a reminder of SN1, right? Here's all the properties of SN1 right here. As a friendly reminder, this was from the first page of our chapter 7 notes, right, where I had made flashcards for this. Okay, here's our table again. We know how SN1 reaction work now. Cool thing is we can do it with, besides just alkyl halides. If we have a tosylate group, we can replace this tosylate group. This tosylate group can leave. All right, we can form a carbocation, and then our methoxide can come in and attack, and we can have our racemic mixture where we replace our tosylate, all right, substitute it in with methoxide through an SN1 reaction. So again, we can have SN1 reactions with different leaving groups. It does not need to just be alkyl halides. It can also be an alcohol group. But always with alcohol groups, your first step is you have to protonate it, turn it into water, and then it leaves, and then you go through the process of adding in your nucleophile will attack and add itself in. All right, now again, E2 reactions. Here is a summary of E2 reaction, and here's our table. Fantastic. All right, you can have E2 reactions with different leaving groups. If you have a tosylate, it is perfectly fine. It will just act as your leaving group. You will do the same exact mechanism here. All right, same procedure, same rules apply. You just simply have a different leaving group. All right, the only thing you have to keep in mind is if you're dealing with alcohols, you want to treat it with concentrated sulfuric acid, all right, so that it can turn into a good leaving group like water. All right, when you're dealing with elimination reactions and you have alcohol, you usually want to use concentrated sulfuric acid with E2 and also with E1. Here's a summary of our E1 properties, all right, and traits. And here's a table summarizing once again. Please learn this. All right, now you can have E1 reactions with different leaving groups as well. Our tosylate is a fantastic leaving group. All right, it will leave, and then it's just a great leaving group. So you will do the exact same procedure here for an E1 reaction. All right, your tosylate group will leave, and then you do the reaction. Same here. Now, if you have an alcohol group, again, you want to convert it into water with E1 using concentrated sulfuric acid. So as you notice, for elimination reactions, when we have alcohols, we usually treat them with concentrated sulfuric acid. With SN1 and SN2, if you have an alcohol, you can just use some sort of halogen, like some bromic acid, chloric acid, all right, HX acid, all right? Convert your alcohol group to water, have that leave, and then proceed with your E1 reaction as you usually do, all right? So with that being said, let's do a few practice problems, all right? Please show the arrow pushing mechanism and the major final product, all right? We have here an alcohol group, all right? We have an alcohol group. Where is my pen? Okay, and our alpha carbon, which is secondary, all right? Now, our alcohol group is not a good leaving group. So we will actually use bromic acid here. We're going to take the hydrogen and we're going to make this into water now. All right, so this converts to water. Now this is a good leaving group and it will leave. All right, so water goes bye-bye. And now what we have is a carbocation at that position. All right, we can draw this anyway, really. Fantastic. All right, now what will happen, okay, is what will happen now is your bromine, your nucleophile, well, actually, wait, hold up. Before we get too excited and we attack our nucleophile, all right, this is, I misdrew this, all right? When our water leaves, there's no group here, all right? So this is secondary, a secondary carbocation. Can we make it tertiary? Absolutely. We can move the methyl group here, carbocation rearrangement, and what you get now, all right, is a tertiary carbocation. All right, now since we want to draw the final product, we don't have to worry about the product that is formed from the secondary carbocation. Let's just worry about our tertiary carbocation. Now our bromine can come in and attack and place itself there. And what we get is this as the final product. Now, I want to make a few notes here that might have been confusing when we were covering, right, how to deal with different groups. All right, if you see, right, like bromic acid. Oh, that's a loud car outside. Let that pass. Anyways, if you have bromic acid or chloric acid, right? All right, these are good indicators. These nucleophiles are good indicators of substitution reactions here, especially when you're dealing with alcohol, with alcohols present, right? We're not dealing with alkyl halides now, we're dealing with alcohols. So alcohol groups in your starting material, all right, and you're treating it with some sort of HX acid, all right, you want to think substitution reaction, okay? So that's how you figure that first step out. All right, you have an alcohol group and you have an HX acid. So this is going to be some sort of substitution reaction. All right, now is it SN1 or SN2? All right, that's a good question. If your alpha carbon is primary, if your alpha carbon is primary, all right, then it will be SN2. If your alpha carbon is secondary or tertiary here, then it's SN1. This is strictly for having alcohol groups here instead of alkyl halides. Very important note to make. This is why we proceeded through an SN1 reaction. All right, our alpha carbon was secondary, okay, and we had HX acid, right? Bromic acid here, for example. So we knew it was a substitution reaction, and because the alpha carbon was secondary, it was SN1. If our alpha carbon was primary, it would have been SN2. So a slight shift in rules here, all right, but same principles. All right, so make a note of that. Fantastic. Let's do another practice problem. All right, here we have concentrated sulfuric acid as our nucleophile. All right, and we're dealing with alcohol group. Alcohol group and sulfuric acid, this is going to tell you that we're dealing with elimination reactions here. All right, we're dealing with elimination reaction here. Okay, now if your alpha carbon is primary, all right, you'll deal with E2. If your alpha carbon is secondary or tertiary, we will be dealing with E1. All right, so that's the rule for this. Now, please show the mechanism with a hydride shift and show the final product. Fantastic, we can do that. Now, this alcohol group is a bad leaving group, which is why we use concentrated sulfuric acid to convert it into water. All right, now that it's water, it can leave. All right, it can leave, and what we have is this secondary carbocation there now. Now, we can have a, a hydride shift, right? So the hydrogen here can shift over. Fantastic. And what we get is something that looks like this. Again, a secondary carbocation. Well, we can have one more. Actually, no, this is perfect. We did our hydride shift. This is what they wanted, right? They said so. With a hydride shift. Cool. Now we can use, all right, our sulfuric acid that is going to come and steal this hydrogen right here, and the hydrogen will dump its electrons here to form the final product that looks like this. All right, and that is our final product after doing a hydride shift. All right, now show both major and minor products of the given reaction. Awesome. Now, we have an HX acid, fantastic, and we have an alcohol group. And our alcohol group is bonded to an alpha carbon that is secondary. Secondary, we're dealing with HX. This is a substitution reaction, specifically SN1, because our alpha carbon is secondary. All right, our alcohol group is going to steal that hydrogen, and we're going to form water there. Perfect, because now this can leave. All right, and after water leaves, what we have is a secondary carbocation. Now, we're not going to do any hydride shifts because, well, actually, we can do a hydride shift if we wanted to. We're going to draw both major and minor products here anyways. So, I mean, if you do a hydride shift, what you will get is still a secondary carbocation, but this can actually potentially give you products here. And so you might get, right, iodine here. All right. Now, if you treat this secondary carbocation, what you will get is your iodine here. And actually, this is a chiral center, so you'll get a racemic mixture. So you're going to have 3 products here. Now, the only reason we don't continue to do more hydride shifts is because this is symmetric. All right. And there's no need for that. Right. You'll just keep getting the same product. Now, for this one, show both major and minor products of the given reaction. We have alcohol group here, no more alkyl halides, and we have sulfuric acid. Sulfuric acid, this is going to indicate elimination reaction here. All right, and our alcohol group is bonded to an alpha carbon that's tertiary. So what we're dealing here with is E1. All right, so our alcohol steals that hydrogen. All right, fantastic. It's now water. And it's going to leave. All right, our water is going to leave. And so what we get now is a tertiary carbocation. Beautiful. All right, now we have beta positions. Now we have to go through our normal elimination procedure, right? Where are our unique beta positions? This is one unique beta position. This is equivalent, so we're not going to count it. These are two same beta positions. They're just methyl groups bonded to the same alpha carbon. And this is a beta position. Now, this beta position is a methyl. So if we do an elimination reaction at this beta position, the product we get is just a normal elimination reaction that forms a double bond there. All right. Now, if we do a if we do elimination reaction at this beta position, I'm going to highlight it in red. All right, what we get is we have 2 hydrogens here. All right, 2 hydrogens here. So we may be thinking to draw the cis and trans product. Let's just go ahead and do the first. Just do a simple elimination and form a double bond here. All right, there's 2 methyls on this carbon, so really there's no cis and trans. This is our only product for those 2 hydrogens here, just because there's no distinguishing feature to do E and Z and then draw the opposite. All right, so these are our 2 products here for this reaction. All right, and that is all I have for you. These are just some random notes I left here about helping you identify, right? When you have alcohol group and you see an HX acid, you know you're dealing with substitution reactions. If you see concentrated sulfuric acid, you're dealing with elimination reactions. All right, I hope this was helpful. Let me know if you have any questions in the comment section below. If you need help, if you want to see even more practice problems for Chapter 7, send me your problems. I can make videos just working through problem sets some more if you would like that, if you would like to see more of that. Other than that, good luck. Happy studying. Have a beautiful day.